So I'm going to start with a quote from Henry David Thoreau that said, "It's not what you look at that matters, it's what you see." And this question of what you can and cannot see has been in our minds for a very long time. In fact, it's closely related with the world we live in and with the scales that we deal with. And just to give you a perspective of these scales, I would like to invite you to travel with me, starting at the cosmic horizon, about 50 billion light years from Earth. And as you travel at the speed of light through space, that is at 300,000 kilometers per second, we see a bunch of things that you cannot imagine. We see superclusters, we see galaxies, we see stars. Some of them have been already dead for a very long time. We have seen planets, we see comets. Yet, these distances from Earth, we still don't really appreciate the dimensions of these scales. So we need to continue travel towards Earth, and eventually we pass the barrier of the 5 light year, we pass the barrier of 1 light year, and only when we are close to our solar system we start to appreciate what these scales mean. So when we get to the solar system and we look at the sun, where the light takes about 8 minutes to travel to Earth, or actually the moon, where the light takes only 1 second to arrive, and then finally we are at our planet. But there is actually another scale, a completely different scale that you probably have never heard of or have never seen, and actually the small scale. At the small scale, the world is completely different. So if we zoom in into our planet, for example, into the city of Venice, we start to see many different things. So if you zoom in, you can see, for example, a droplet of water, and inside that droplet there is actually a bacteria. And you can zoom into the bacteria, and you see DNA. And we can zoom into the DNA, and you start to see atoms. Atoms vibrating in place at room temperature, but you can still zoom in further, and you actually, inside the atom, you see the electron cloud, and at the very center of the atom, you see the nucleus, where you see protons and neutrons, but you can still go further in, and you see quarks. Interestingly enough, from the beginning of mankind, we have been interested in looking at the universe. And therefore, we develop instruments like this first telescope to understand the universe. Of course, nowadays, we have a better one. We have the Hubble telescope that can survey, that can probe space, and can take beautiful images. One of them is actually shown here. It's called the pillars of creation. And this is where stars are actually formed. And the stars are an interesting thing because they are like nuclear reactors. They actually, during their life, they actually create chemical elements like hydrogen and lithium and helium. But then at some point, there is actually an explosion. Let's see. Not passing. So at some point, these stars actually go through a massive explosion. And during this explosion, all the other chemical elements are actually formed. So everything you have learned in school, which is actually shown in this it's not turning. Which is shown here, which is the periodic table. Everything you see there was made by stars. And so it's not surprising that if you look at our chemical body, yours and mine, we find very much the same thing, the same ingredients that you find all over the universe. So I can actually take from my body, I can fill a tank of hydrogen, I can fill a tank with oxygen, I can stack some calcium, some phosphorus, and then you see a lot of elements there, from gold, silver, and even poisonous elements like arsenic inside our body. And in fact, if you go to Wall Street and try to sell this, you get about 100 euros. Are we worth so little? Of course not, because it's the proportion of these atoms and the way these atoms are arranged that allows us to think and dream and walk. So the question is, how small are these ingredients of life, the the ones I've been mentioning. So just to give you a perspective of scale, I'm going to divide the scale in 3 sections, the macro scale. So they have the human being, which is about 2 meters, that is 2 billionths of a nanometer. That's the things we see very well. Then you have the micro scale, that's pretty much what we can see with our naked eye. So you can see the width of a human hair, which is about 80,000 nanometers. And then there is the other scale, the nano scale, the very small scale you cannot see with your eyes, that goes down to about the atomic scale. So that brings us into the nano world. And here, the interesting question from Feynman. Richard Feynman was a physicist. He won the Nobel Prize. And in 1959, he asked this following question. Can we write the 24 volumes of the encyclopedia on the head of a pin? That seems completely out of proportions, so we can do a bit of engineering. If I take a head of a pin, which is just about 1.5 millimeters across, and multiply by 25,000 times, that gives me the pages of the 24 volumes of the encyclopedia. So now I can do reverse engineering. I can take a single dot of that encyclopedia, which is about 0.2 millimeters, and divide by 25,000 times. That gives me about 32 atoms. So in other words, if I can write one dot of the encyclopedia with 32 atoms, I can insert 24 volumes of the encyclopedia on the head of a pin. And in fact, I can do much better today. I can write it at atomic level, and you see here the word Star Trek, where every single white dot that is there is a single atom. So that brings us into the Nano Age, which asks the following question. What about if we could assemble the basic ingredients of life that I've been talking about the way the nature does it, which is atom by atom and molecule by molecule? And to give you an example, here's 2 types of molecules, a green one and a pink one. The pink one doesn't like the green one. You place these molecules in a solution, don't do absolutely anything, and they start rearranging. Of course, the greens like the greens, so they start aligning each other. The greens don't like the pink, so they push them away. And you see that by self-assembly, without any kind of human intervention, these films start forming. These are actually lipid films that we actually have in our body. And see, this is called self-assembly. Another example is shown here. If you have carbon in certain conditions, you can make these carbon nanotubes. Again, completely by self-assembly. You don't need any human intervention. And this self-assembly of carbon nanotubes produces these very remarkable structures. You can see one of them here, taken with the electron microscope. And these have incredible properties, about 30 times stronger than steel, and with electrical conductivities about 1 million times a typical copper we use in our eyes. With these tubes, we can do some funny things. For example, here you can see 2 tubes connected by some ligands, and you can see they are speeding at about 70 gigahertz. Now, to give you a perspective of these rotations, if you're taking your car at about 100 kilometers per hour, the engine is rotating about 3,000 rotations per minute. We are talking about here 70 billion rotations per second. Now, with that, you can actually make devices. So with gears, you can make motors, and with motors, you can make devices. And here's one that you can send into your blood vein if you have some kind of illness. And these machines will go into the blood veins. For example, in this case, it's picking up cholesterol. And so an interesting question would be who is controlling these machines, because they're actually by the thousands inside your body. But this is kind of where we're heading. So this is kind of surgery where the surgeon is inside your body instead of having some kind of cutting and doing things like that. So the question then is, how is nanotechnology shaping the world? And this is happening in 3 different fronts. First of all, of course, in the digital domain, the Internet of Things, where everything is connected, and where actually the objects become subjects. And to give you a perspective of what happens in 60 seconds at the Internet, you have, for example, 527,000 photos shared. You have about 2.7 million visualizations in YouTube. But you have to understand that for this to occur, underlying technology is actually silicon that is shown here. So silicon is a semiconductor. You have this wafer of silicon, and now you're printing the circuits. These are actually the basis of all the computation you see and all digitalization. These are the transistors that were invented in 48, but now they can be done at very, very small scales in 3 dimensions. And in fact, in a square centimeter, you can have about 30 billion transistors that you have in a single chip. And this is actually, just to give you an idea of this, so this is a needle, and you have all this technology impregnated in your silicon. This is actually the base of all the digitalization that is happening today. Also, in terms of materials, there is new materials that are coming in. This is graphene, for example, a single layer of carbon that actually very interesting properties. For example, it will allow you in the future to have flexible electronics, so you can look at your cell phone in the future, it will look like that. Or because this graphene is extremely strong, you can make, for example, aircrafts that look like that. So you might be scared or not, but at least you can look at the sky, you can see the clouds, and this, you have a much more open situation. And then, at the biological domain, something is also happening. What you're seeing here is 3D printing of human tissue. In fact, muscle tissue in real time. So we are actually printing already human tissue. And of course, after this is done, you have a bit of a muscle. And the muscle is actually showing you here. And of course, as a muscle do, it contracts. So this is actually a good example of 3D printing in the biological arena. So all the nanotechnology is actually promoting all these areas. And so you might ask now about the future. There is, of course, questions that are relevant. Are we going to be more human-like or machine-like? Are we going to be able to do teleportation? In other words, I just need to do a copy of someone and I appear in Japan. Of course, are we going to have printed cell phones? And that's going to be coming soon. And then maybe most disturbing is the fact that we can genetically code human beings. And of course, with that, there is a lot of ethical questions that come about that we need to understand. So before I finish, and just to show you the level of manipulation that we can do nowadays at the atomic level, I'm going to show you a little movie from IBM, which is shown here. It's called A Boy and His Atom. And each dot there is actually a single atom. Perhaps you could put the sound. Thank you very much.